Hello, friends. Our story today begins in the 1700s. At the time, many physical phenomena, such as heat, magnetism, electricity, phlogiston, or combustion, and light, were thought of in terms not as how we think of them today, but rather as ether fluid that flowed between objects and through solid objects. Today, outside of crackpot circles dominated by conspiracy theorists, ethers have largely been replaced with models of particles and forces. While light was probably the last holdout of the imponderable fluid models, that was up until the work of Michelson and Morley, it is electricity where the least work has been done to replace the fluid-based vocabulary. The terms that we're about to use, current, flow, all stem from this archaic idea that electricity was a fluid. Charles Francois de Cisternay Dufay posited that there were two types of electrical fluid, vitreous fluid and resinous fluid. Vitreous electrical fluid was the kind of charge that was acquired when glass was rubbed with silk, vitreous coming from the Latin for glass. Resinous fluid would be the type acquired when amber was rubbed with wool, amber being a form of resin. So, similar to your own triboelectric lab work, Dufay experimented with small pieces of foil, and he charged them up with both of these kinds of electrical fluid. So he would rub a piece of amber on wool and then touch the amber to one of the foils in order to give that foil a resinous electric charge. And then he would rub glass against silk and touch the glass to the other piece of foil in order to give that a vitreous electric charge. And then he observed that the two pieces of foil would be attracted to each other. But if he charged both of the pieces of foil the same way, they would be repelled. So he arrived at the idea of these two separate types of electrical fluid. He also hypothesized that they were separated by frictional forces, and when they recombined, having both types flow onto an object, then they would neutralize. Benjamin Franklin, one of the most interesting men to have ever lived, and arguably the first truly American man, was one of the first to argue for a singular type of electrical fluid. His idea was that it was one type of electrical fluid, and the different effects were different states of pressure for that fluid. This replaced the then current distinction between vitreous and resinous with the terms positive for high pressures of electrical fluid and negative for low pressures of fluid. For example, when glass is rubbed with wool, the resinous fluid was actually just a dearth of the electrical fluid on the glass caused by it transferring its electrical fluid onto the wool. Thus, you would have an equal and opposite charge on the wool. You can see how this moves us kind of closer to the current understanding, but it was not a slam dunk. The debate between single fluid and two fluid theories raged heavily for a century, but Franklin's idea was so influential that it still permeates the ways we describe electrical current to this day, including most famously his idea that a buildup of electrical fluid or charge should be called positive. And then as the charge flows away, it goes toward negative. This creates a problem with the modern understanding because you and I know, having the benefit of living in the future relative to Benjamin Franklin, that it is electrons, not fluid, that is jumping from place to place. And electrons are known to have a negative charge. In reality, electrons are what is moving, but the convention still remains when we talk about current. We talk about it coming out of the positive side of the battery and flowing toward the negative. So conventional current is opposite of true motion of charges. That goes to show you something about how influential his description was, that even though we know it is straight up the opposite of correct, well, we just refuse to move on. Speaking of moving on, building on that fluid analogy, imagine a large container of water. Imagine that it is relatively full. I'm not going to color the whole thing in, that'd be silly. But at the bottom, it connects through a pipe. There is a valve here. And the pipe goes to a neighboring container of water, which is empty or nearly so. The water here, before this valve is cracked, it's been pooled together and it has a certain amount of gravitational potential energy. This water would love to be on the ground. But furthermore, it is weighing down on all of the water beneath it. That water is pushing back and against the sides of the container. So this is a high pressure situation. This water is built up and the particles collide with each other. They collide with the walls of their container and they very much want to escape. They have this gravitational potential energy where they want to fall down, but they can't do that. This high pressure, well, it has nowhere to go until we crack this valve open. Once that valve is cracked open, of course, water will flow through and begin filling up the other container. At what point will the water stop flowing? Will this one be completely empty and this one completely full? No. They reach equilibrium. It is when there is no difference between the two in terms of water pressure that the water will stop moving. Water does not go from high concentration to vacuum and leave behind a vacuum. It equalizes. Now, imagine instead that we have a battery with a positive and negative terminal. You connect a wire to the positive terminal, to a switch to the other side of the battery. Now, forgive me, I know it's not right, but let's use the Franklin convention. You've got all of these positives built up over here. That's why they call it the positive terminal. All of these positive charges repel each other, creating, very much like the water molecules beating on each other, you can think of it like a pressure. As soon as the switch is thrown and connected, what we call closed, all of those positives will flow through and they will go to where there is a lack of positivity. And this negative terminal, in addition to there being a high pressure here and a low pressure here, it's also attracting them along. But in this case, the water supply has a high pressure and the water height gives gravitational potential energy. Here we have effectively kind of an electric pressure, repulsion, and an attraction. So there is electric potential. So energy is available to get them to start moving. And this water flows through a pipe. Here, charge flows through a wire. There is an element here that can make or break the ability to flow. And the water analogy works relatively well. What would also be interesting would be to have some sort of like water wheel so that as water flows in, this wheel spins and maybe it's attached to something like doing work. Water wheels historically have been used to grind grain and turn saws at sawmills. Here, we could always just attach a good old-fashioned light bulb. In this case, the water's energy is being taken out. Its kinetic energy is basically doing work to spin the wheel, and then the wheel does work on whatever it's attached to. Here, the energy is being taken out by the filament of the light bulb and kind of used up. The electrical energy is turning into heat. The filament eventually gets to be red or white hot, and it glows, and there's an energy loss due to that. Now, why did the water flow here? A difference. Why does the charge flow here? A difference. And that difference is, of course, our electric potential. This is familiar from the previous unit. Now, as electricity started to be installed in houses in the late 1800s, early 1900s, uh, it became something that was not just the domain of scientists, but of construction workers. And that led to some simplifying of the terms, similar to how your car's amount of miles traveled. No person in like lay conversation is going to call that the displacement of your car. They're going to call it the mileage. Well, this is also called a voltage. The volt unit is named after Alessandro Volta, who was the first person to build a chemical battery. Rather than what Dufay and Franklin had done, which was to have electricity be constantly generated by friction, 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 friction. Alessandro Volta made this, well, literally a pile of metal discs of alternating types of metal, and between them sandwiched were pieces of paper or cloth soaked in salt water. And electrons were pushed up to one side of the pile and away from another side of the pile. And it was a primitive chemical battery cell. This is why sometimes batteries are called voltaic cells. Not just that they provide volts, but they are also first introduced by a guy named Volta. We will define electric potential as the work per charge done to move charges through an electric field. A simpler way to think of it, especially when you are dealing with a battery, and that kind of jives better with this analogy, is to say that it is the difference in charge across a circuit. When there is no difference in pressure, the water stops flowing. When there is no difference in charge, when this side is just as positive as this side is, the flow would stop. It is a common misconception that batteries run out of charge. Batteries don't provide charge to a circuit. Batteries give the charges that are in the wire already a reason to move. And that is a failure of this model. In reality, the electrons are already in a wire when it's neutral. The electric potential simply gives them a reason to jump to the next atom. And a more accurate analogy for this would be a Rube Goldberg machine. You're familiar with Rube Goldberg machines? I know Joe has iffy ideas about what a Rube Goldberg machine is. Have you ever seen those videos where somebody knocks over a domino that hits a series of dominoes, and then it moves a toy car, and then the toy car hits a trigger that shoots an arrow that pops a balloon, and the balloon releases a thing, and da 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 da. Well, this gives the first domino a reason to move, and then that domino hits the next one, the next one, the next one, the next one, the next one. Here is some sort of contraption in the Rube Goldberg machine where it can do some work, and then dominoes again. In terms of an equation for voltage, should be familiar. 1 volt is defined as 1 joule per coulomb. There is an archaic term which sometimes appears, depending on who's writing your physics stuff, electromotive force. Of course, this is not a force. Otherwise, of course, we'd be measuring it in newtons. But electromotive force was an early understanding of this. Like, this is the force that pushes them to move. Now that we have the idea of energy, it's the work provided to get them the kinetic energy to move. But if you ever see the notation for a voltage as a lowercase epsilon, well, now you know why. If you ever see it, don't say I sent you into it unprepared. Now, the flow would be an electric current. Current is the rate of charge flow through a circuit over time. The circuit is, in this case, the path from one side of the battery to another. Wire into the switch, across the switch, more wire, through the light bulb filament, out of the light bulb filament, into more wire to the battery. Whatever path it is across the voltage, that's the circuit. Current gets the symbol I. I know what you're thinking. Shouldn't it be C? But C for Coulomb, C for charge, C for speed of light. Eventually, we got to use other letters. So we end up using I for intensity of flow. The units for charge, read the definition really literally. A rate, it's a fraction, over time. So I equals Q over T. Sometimes you see those written with deltas. I'm not going to bother. Current equals the amount of charge transferred per given amount of time. So coulombs of charge per second of time. Easy stuff. Unsurprisingly, we have this combo meal of units, and we name it after somebody who did something interesting, and in this case, ampere. Frenchman who did a bunch of early work with electromagnetism. As we get into the magnetism unit, we'll get to Ampere's law. But 1 ampere is defined, well, it's actually defined as a fundamental base unit. It is a base unit, like the kilogram isn't defined in terms of other stuff, or the second isn't defined in terms of other stuff. It has a definition outside of the units and comes from, whatever the flavor of defining our metric system units for this century is. In the past, it was like a kilogram was the weight of a liter of water. Then there was a specific metal ball in a basement in France, and now it's defined with physical constants. Well, 1 amp is a base unit like that. But 1 ampere, Americans usually call them amps, 1 ampere is 1 coulomb per second. So rather than saying 1 ampere is defined as 1 coulomb per second, the real truth of it, amps and seconds are fundamental base units of the metric system. Coulombs are defined as the amount of charge that flows through a circuit when you run a 1 amp current for 1 second. In the past, I've had students affectionately refer to this formula as I quit. I would have thought I equal cute, but I quit seems to catch on more so. Now, in experimenting with voltage and current, you will find what Georg Ohm found. Georg Ohm, with a name like that, you can tell he is a German physicist, Georg being the German equivalent of the name George. But in his experimentation with what was then called electromotive force and current, Ohm found a linear relationship. So Ohm's law is that the current through a circuit is directly proportional to the, again, he wrote it as electromotive force, but the electric potential, and if you want to switch it up again, you could just write voltage across the circuit. If you do an experiment and you put your experimental results on a graph, if you get a line or a curve and you find the equation of that line or curve, that's how you make the equations for physics. Experimentally, and these aren't his actual results, but rather a simplification thereof. So you take a given circuit and you put 1 volt across it. And let's say that that 1 volt gets you 1 ampere. Well, 2 volts gets you 2 amperes. 3 volts gets you 3 amperes. 4 volts gets you 4 amperes. 5 volts gets you 5 amperes. Connect your dots. If you were to actually do this experiment, you would of course use a line of best fit, but this is, theoretical where everything is perfect and easy. And the slope of that line, 5 volts, 5 amps, is 1 volt for every ampere. But let's try a different circuit. So we take our variable voltage source and our ammeter to measure the amount of amperes. And in this circuit, we find that applying 1 volt gets us 2 amperes. 2 volts gets us 4. And the slope of this line, half a volt per ampere. In other words, every volt gets you 2 amps. Here, every volt got you 1 amp. So there was less flow per volt on this one, if you flip it. Then we try one last time with yet another circuit. So we take our variable voltage source, we take our ammeter to measure, and with 2 volts, we get only 1 amp. With 4 volts, we get only 2 amps. And in this case, the slope of that line, it takes 2 volts per ampere. Now, which one of these circuits fights against the voltage least? This one. A little bit of voltage gets you more flow. This one, it takes 4 times as much voltage to get the same amount of current. So this one works against the current less. Why? Well, there could be a number of reasons. The circuit could be made out of a better conductor, a more conductive material. Maybe this one is, let's say, copper wire, and this one is tungsten or steel nail or something. but the material in your circuit is going to affect how well electrons can do that dominoes tapping into each other thing. Because again, that's an analogy. What is actually happening is that an electron jumps from one atom to the neighboring atom. Well, if the atoms are very permissive of, hey, the electrons, they can just go, well, then it takes less voltage to get them to hop from atom to atom. If the atom's nuclei have a great pull on their electrons, they're not going to let them off as easily, and it's going to take a lot more electric potential to knock them out of the atom and into the neighbor, where then that neighboring atom can let go of one of its. This quantity is called resistance. So resistance is what we were measuring in these slopes. A measure of how well current flows through a circuit. In short, a better conductor yields a lower resistance. So that I don't run out of room to write it again, let's give it a symbol so that I can abbreviate it. And unsurprisingly, the symbol is R. We found the resistance of these circuits by a line with y-axis, the rise being voltage, and the x-axis, the run being current. Slope is rise over run, so resistance must be voltage over current. Now, of course, you can algebra this any way you'd like. V equals I times R is an extremely common way to write it. Uh, it's kind of like Newton's second law, where force per mass equals acceleration makes the most sense to me, but F equals m times a seems to be the version of it that got into the zeitgeist. Well, ver is the probably most common way you see this written, and may or may not be how it is written on your equation sheet. Of course, you could also do voltage per resistance determines the amount of current, and that also kind of jives with the force per mass determines how much you accelerate. Or you could do what most aspiring electricians do, and you could use your cheater's triangle and let it do the algebra for you. V over I solves for R. You just cover up whichever one you want to solve for, and you get the equation. A key important thing for you to remember. Any component in a circuit, I don't care whether it is a light bulb, a wire, a motor, a speaker, any component in a circuit that uses energy adds resistance to that circuit. So we often talk about resistors. A resistor is a part of a circuit added specifically to create a voltage drop, suck up some of that energy, and drop the current. That way you don't blow a circuit. Or if you have a variable resistor, you can control the amount of current to your liking. But not all resistors are necessarily things that are just added as speed bumps for your electrons. A motor is doing work. You think of that as something useful. Well, it's still adding resistance, and you have to treat it as a resistor because it uses energy. And remember, the greater the resistor, the more energy it uses up. Oh, no, 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 no. It's starting to sound familiar. The use of energy to accomplish something, that's work. And if we're talking about doing more work and current is time sensitive, work and time, put that together in your mind, brain, and you get power. Remember that power is the rate of energy usage. That should still be reasonably buried in your folds of the gray matter, but power is the usage of energy over time. Power is your change in energy over time. This is old news, but where have we lately seen energy? In which of the equations in the video so far? You're right. You're right. It's the voltage. So energy can be found from voltage times charge. Make that substitution, and this turns into power is voltage charge per time. Charge per time sounds kind of familiar. When have we recently seen charge per time? Yes, I quit. So our final transformation of this, power is current times voltage. So you will often see questions about resistors in terms of how many seconds would it take to release this many joules? Da, 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 da. If it's a power question, this can help. This, we will make a note, is our electric variation of the power equation. Now, if we take Ohm's law that we have the cheater triangle for here, we could make further substitutions and derive all sorts of fun versions of the electric power equation. So if we start with PIV, and we take Ohm's law set equal to voltage. Voltage is current times resistance. So we could derive an expression for power when the voltage is not known, but we do know the current and resistance. I squared times R. If that is PIV and that is Ver, then would this be here? I don't know. But a useful expression. We come back to PIV. And instead of a situation where we know the current and the resistance, maybe we know the voltage and the resistance, but the current isn't known. Now you could, if you know the voltage and the resistance, you could just find the current here and then plug that into PIV, and you could two-step it. Or you could one-shot it by substituting in that step. And power would then be equal to voltage times voltage over resistance. You connect a 50 ohm resistor to a 9-volt battery whose internal resistance is 1 ohm. Only now am I realizing that I don't think, looking back on the previous page, I remembered to do my usual thing of telling you the units for resistance. So I guess I have to double back on that. But the units of resistance named for Georg Ohm, who formulated that law we were just talking about, are ohms. Since whenever you have a unit named after a guy, it's always their initial capitalized. Why do you think we don't write this as 50O? Because then it's just going to look like 500. So we do the usual thing and go to the Greek alphabet and use a capital omega. Well, it makes the same O sound that's at the beginning of ohms. So makes sense. And 1 ohm is 1 volt per ampere. So now that that's cleared up, 50 ohm resistor to a 9 volt battery, and the battery has an internal resistance. Now, an ideal battery, we often just neglect to think about the internal resistance, but a real battery does have some resistance to flow uh, because, it's made out of stuff. Anyway, here's how you would work with that. The current through the resistor. So the current is what we want to know. The electric potential supplied is 9 volts. And what is the resistance of the circuit? Well, we have a 50 ohm resistor, and then 1 additional ohm is incorporated into the circuit just from the battery. So we have 51 ohms across the circuit. We use Ohm's law. When you set it equal to current, it is voltage divided by resistance. 9 volts for 51 ohms gives us a current of around 1/5. 9 divided by 51, according to my calculator, 1.765 amperes, or considering those are somewhere between 1.8 and 2, or 0.18 and 2 amps would be a reasonable place to round it. Now, in modern electronics, in order to not hit huge powers where they have to suck up lots of energy in order to function, you're shooting to have tiny currents. So often, when you are working with realistic circuits, like the inside of your phone or a guitar pedal or something, you usually see stuff rated in milliamps. Now remember, milli is 10 to the -3. So if we were asked for this in milliamps, we would write 180 milliamps. Determine the electric power dissipated by the resistor. So power is our unknown. The resistor is 50 ohms. Now notice this says the resistor, not the whole circuit, so we just go to the 50 ohms of the resistor, and we know that the current through that resistor, it's never a good idea to round before you get to the end of the problem, so I'll use the unrounded, well, less rounded version of this. So we have PRI. You're thinking, could I have used the 9 volts? Not really, because some of that 9 volts got used up to get through the battery itself. The current is the same everywhere. We'll get to the rules for that later, but follow along for now. Right now, we're just taking our equations for a test drive. We'll get lost in the details another time. So which one of our electric powered derivations best jives with what we were asked for and what we were given? We know PIV, and this would get rid of the voltage that we don't know if we screwed it around. So here, I squared times R is the one we want. 50 ohms, 1.765 amperes squared. Again, three variable algebra, not hard. Plug it into your calc. That's short for calculator, chat. Times answer squared times 50, because I still had that on my calc. That's short for calculator. And I got 1.557 amp squared ohms. Do you remember the units for power? If you don't, I'm going to be upset with you. It's watts. So about 1.6 watts. Would a 10 ohm light bulb replacing that resistor dissipate more, less, or the same amount of power? Well, what went into power? Power is current squared times resistance. And if we drop this resistor and replace it with something of a lower value, literally 1/5 the value, what does that do to the entire current? Well, you could either math it out or think it out. For those of you who are willing to do it proportionally, if resistance went down in the circuit, current goes up. There's your answer. If this goes up and then it gets squared, who even cares about that value? You know this is going up. Well, let's try. Going back to Ohm's law, voltage divided by resistance is current. 9 volts divided by 11 total ohms to figure out the current through the circuit. 9 per 11 gives us a current of 0.82 amperes. All right, so the current went way up from 180 milliamps to 820 milliamps. That's a massive jump. So 0.82 amperes times 10 ohms. Well, the question is, this went down to 1/5, which means that we got 5 times the current. Yeah, it's 1/5, 5 times. Okay, so 0.18 times 5. All right, this is close enough anyway after we've rounded. This is 1/5 of the old value. This is 5 times the old value, and then it gets squared. 25 times 1/5. We better get a power that's about 5 times larger. Squared times 10. And we get 6.69. Nice. So 6.7 watts, 1.6 times 5. And with some rounding slop, we're pretty close. All right. Well, that is some practice for these. Obviously, you're going to get more questions from me on a sheet. But I think a question that would be reasonable of you to ask me rather than me asking you, what goes into making a resistor resist? Well, I hinted at it a moment ago with the idea of different nuclei holding on to their electrons with more or less tenacity. Every material, and you'll remember this from chemistry, I'm hoping, has a different electronegativity. Is this ringing a bell? Electronegativity? So resistance is basically just a function of that. I mean, there's some other stuff too. Once you scale it up from just having one atom as your conductor, but to several. But resistance, first and foremost, is going to depend on your material. The electronegativity, how well it holds on to the electrons, whatever you want to call it, the material matters. And the resistance effect of the material is measured, at least in our class, as resistivity. Resistivity gets the symbol that makes the sound R in the Greek alphabet, a nice lowercase rho. If you're thinking, why is it not capitalized? Because if it was capitalized, it would just be a P. Isn't that just P? No, it's curvy. Duh. But for this, metals and other good conductors have low resistivity. Why? Well, put frankly, they suck at holding on to their electrons. They will happily let them escape. It does not take a lot of energy to boot those electrons out of an orbit. The better something is at holding on to its electrons, the harder it is for stuff to cause a flow of electrons through that material. So insulators like rubber, cloth, air, water that doesn't have stuff dissolved in it. Salt water is an okay conductor. It's not great, but it's okay. But pure water is a terrible conductor. Insulators have high resistivity. So as you see, there's more than just pure electronegativity that matters for this, like I was saying about how water, when it has stuff dissolved in it, and also temperature can have an effect on resistivity. Um, but that goes into the measurement of resistivity. So if you're given rho, it's already been addressed for you. The second thing that resistance of a wire or a filament that is acting as a resistor would depend on is the length of the sample that is acting as a resistor. And usually this is phrased as like the resistance of a wire. So the longer the wire, the greater the resistance. As it goes, a little bit of energy is eaten up by every single atom. So the more atoms in your Rube Goldberg machine of tipping dominoes, the less energy is left over to flow at the end, and that slows down there, and therefore it slows down everywhere else because there's a traffic jam. So length of the wire does matter. I use a cursive L for that, and you should too, so that you don't mistake it for a 1. And finally, the cross-sectional area of the wire. Not the area of like the cylinder that the wire is, but the cross-sectional area. In other words, how fat the wire is. A wider wire yields lower resistance. Speaking of traffic jams, if one lane is blocked, but you got more lanes, you can just go into another lane, and that's going to fight you less. So a fatter wire has more atoms at any given point to like hop over to if there is some resistance met. Pardon the pun. By the way, while I'm thinking of resistance, you will sometimes see measurements of ohms on like the back of speakers, but they won't call it resistance. If it's listed, they'll call it impedance. This is getting a little heady, but the short version of it is resistance is what we call it for direct current. Like a battery provides direct current, pushes through in one direction from the positive terminal to the negative terminal if you're using the Ben Franklin conventional current thing, or the electrons are flowing from the negative to the positive if you are a realist. But either way, it's one direction, depending on how you define that direction. Impedance is like resistance, but for an alternating current. There's a little bit more that goes into it. It's not just resistance, but also something called reactance, how well it deals with the alternation of the current. But we're working on resistance. Impedance is something that you would get into and more in the college level. A common lab for this, and I used to do this. I don't think Play-Doh is still electrically conductive, but because Play-Doh has got salts in it and it had water, it used to be kind of conductive. I've tried it recently, and I just don't think they make Play-Doh the same way anymore. But you could teach like first graders about electrical resistance with Play-Doh. It was awesome. You get them to roll it up thin and long so that here is the length of your Play-Doh wire, and there is your cross-sectional area. And then you have your first graders with their conductive Play-Doh. Go shorter with it for less length area. Stick a battery on either end, a light bulb in there somewhere, so that the brightness of the light bulb would correspond to the uh, magnitude of the current or the intensity of the current. And you would find quickly that a long, skinny Play-Doh wire gives you a dimmer light bulb. It is working against the current, so we say that it has high resistance. Whereas a fat, squat, short Play-Doh wire would give you low resistance. So taking those proportions and making a quick equation out of it, if you don't happen to have a battery and an ammeter nearby, but you still want to find the resistance of a wire, if you know what it is made out of, how long it is, and you remember how to find the area of a circle, and it's roughly circular, you get a decent approximation of it. Please, please, please read these problems carefully so that you don't mistake resistivity for resistance. That's a rookie mistake, and it's the kind of thing where you kick yourself for it, and because you lost the easy points. You should have not gone as fast. You should have paid a little bit more attention. There will be more practice problems on the sheet you get, but for right now, I'm cutting this video off so that I can go to sleep. It is 11 o'clock on a Sunday night, and Boba and I are signing off. Adios, kids.